And I guess maybe I should start by asking whether there are any questions which have come up overnight since I finished yesterday's lecture. Is there anything anyone wants to ask about to start with? Right. Yeah.
So the width of the plateaus is determined by the
Right. So the width of the plateaus. So in a single particle picture, as in fact I'm going to talk about probably in the beginning of the lecture tomorrow, depends on temperature, and as you go towards the low temperature limit, then the plateaus should take up the whole of the trace as a function of filling factor. So that's to say the steps between plateaus shrink in width as temperature goes to zero. I should say that in very high mobility samples where interactions play a crucial role, then things are a bit more complicated and you can easily find data that looks different from what I just said, but what I said is the basic picture. Yes?
It's clear there's no singularities in the density of states, near the middle of an end level in the presence of disorder.
There are certainly strong reasons for believing that's not the case. I mean, in general, in disordered systems, to have a singularity at a particular energy, you'd probably need some symmetry that takes that energy out. And here, with the kind of disorder that we imagine adding a random potential, there's no way to get a symmetry because you could have a region where the average potential is lower or higher, when the local average is lower or higher than the global average, and so any kind of singularity would be smeared out. And there are, in fact, some models where you can work out the density of states exactly. For example, if you have Gaussian white noise disorder, and from those exact solutions, you can see that there isn't a singularity. Okay, so let me start with the new material in this lecture. And as you remember, the idea of localization took us to a paradox because if most of the states are localized, then it becomes hard to understand how the remaining extended states carry the same Hall current as in a clean system. And that's a sufficiently interesting paradox that it's worth looking at it from different viewpoints. And in the last part of the lecture yesterday, we looked at one viewpoint, which is in terms of edge state transfer. In this lecture is give you two other viewpoints. One involving what's called flux insertion, and the other involving chain numbers. So let me start with flux insertion. So this is some work that Laughlin did shortly before the discovery of the fractional effect and shortly before his theoretical work on the fractional effect. So the basic idea here is to study a sample which is in a different geometry from the Hall part that I was talking about. And it's sort of part way to a theorist geometry, but it is actually one that can be realized experimentally if you're sufficiently interested to do it. So it's a sample that's on the plane, but in the shape of a ring, as it's called, Corbino disk. So we have a magnetic field piercing the sample in the usual way to produce the quantum Hall effect, and this is our two-dimensional electron gas. And then the one thing that you do that would be hard to realize experimentally is you'd like to have a current in the radial direction, and if the Hall conductance is entirely off, if the conductivity tensor is entirely off diagonal, you should do that by having an EMF that goes around the circumference, and as a theorist at least, you can generate that by having some flux which is separate from the flux producing the quantum Hall effect, just piercing this hole, and letting it be time dependent. The idea is that time dependent flux Faraday's law, which is the time derivative. And so we'll get a current in the radial direction, which is given by the Hall conductance times the rate of change of its flux. And if we let the flux change for a while, we can integrate up this current and get the charge that's transported in the radial direction, in other words, from the inner edge to the outer edge of this disk. And then we have the transported charge is this Hall conductance times the change in flux. We used to what we by one flux quantum, and then the change in flux.
Is there a minus?
Yeah, there is, but it's not going to be important anyway. Okay, so now comes the key part. If you had some arbitrary conductor here and you increase the flux through the hole by one flux quantum, you wouldn't know anything particular about the relationship between the initial and final states of the conductor, and so you wouldn't be able to conclude anything. But if this conductor is really in a quantum Hall plateau, and as we saw from the experiments, dissipation is in the low temperature limit, then you can assume that increasing the flux slowly will keep it in the ground state. And what's more, you know that if you increase the flux by one flux quantum, then the ground state at the end is the same as the ground state at the beginning. So the only thing that can have happened in this process of increasing the flux slowly is that possibly some number of electrons got transported in the radial direction from the inner edge to the outer edge. So if the cube data is in a quantum Hall state, and the flux increase is adiabatic, then Q is some number which we don't know and won't be able to know at this level times an integer. And then, of course, if I put those two things together, I can say that the Hall conductance is E squared over H times this integer. Which is, of course, the result that you'd like. And it's worth thinking a little bit about how that comes about. And one situation which you can analyze in detail is, of course, the one of a clean system. and then we can describe it by thinking as a function of radius about the potential that electrons see, and then as I was saying for the case of a Hall bar, we represent the inner and outer edges of the sample by some confining potential, so the electrons see a potential like that, and if we choose one coordinate running around the circumference, then in a clean system, the wave vector in that direction will be a good quantum number, and we can characterize states by a wave vector around the circumference, which, in the absence of this flux threading the hole, would simply be 2 pi over the circumference times some integer. And then when we increase the flux, that wave vector will become 2 pi over L times an integer plus 2 pi the flux threading the hole, measured in units of the flux quantum AP. And then these wave vectors will determine the location of the states in the radial direction. So at a given value of the flux, we have some sequence of states which become closely spaced as the system size gets large. And then as we increase the flux, the wave vectors evolve, and because wave vectors are tied to the radial coordinate, the states move like that. So you see that this pumping of charge from the inner edge to the outer edge involves states moving over to take the place of their neighbors as we increase the flux by 1 quantum right through the system. It's actually worth looking at this picture in a bit more detail, because you might worry that if this is really a closed system, and if you really increase the flux strictly adiabatically, then, well, certainly you should return to the same ground state, and if it's a closed system, then it's not clear there's possibility of pumping charge. And if we follow the energies of a couple of these levels that, say, both start out near the Fermi energy, if we follow their energies as we change the flux, then this one on the inner edge will go down, and this one on the outer edge will go up. And so clearly we'll have some level crossing, or more realistically, an avoided level crossing when their energies pass each other. And if you think about the energy splitting at this avoided level crossing, then it'll involve hybridization between states at the two edges. And if these edge states are really localized, then the matrix elements that produce the hybridization will go to zero very rapidly when the width of this Corbino disk gets large compared to the magnetic length. So this is some extremely narrow avoided crossing. And if you ask now what it means to say that we increase the flux adiabatically, you realize that actually we don't want it to increase adiabatically in the strictest sense, because if we change the flux sufficiently slowly, then we'll stay always in the ground state, which means that electrons will tunnel backwards and forwards across the width of the ring, instead of being transported by this flux change. So what we need to do is increase the flux sufficiently slowly that we don't generate excitations in the bulk of the system, but on the other hand, it should increase at a rate fast enough that we sweep across these avoided level crossings rather than following the energy state strictly adiabatically.
I'm sorry, could you explain again maybe why these states are moving in radius as you change the magnetic flux? I think I missed something on this bottom equation in the middle of the blackboard. There's something I didn't understand there.
Yeah. So I'm imagining some things which I didn't write down about the form of the wave function, and some of that's dependent on gauge. I don't want to get too far into the details, but basically I want to think about the wave function as a function of radius and a coordinate around the circumference, which I think I'll call y, because I don't want to introduce other angles at this stage. So if I pick my gauge right, I'll have a dependence around the circumference in the clean system that's ETI ky, and then I'll have some radial function which depends on k. Okay, so then the boundary conditions as I go around the circumference would simply be periodic boundary conditions if this flux is 0, and if it's non-zero, then it's boundary conditions with a twist, which is represented in this way. So as I increase the flux, the wave vectors increase. So that's half of it, and then the other point is that if you look, say, at the expectation value of the radius in these functions, then it turns out to be related to k, so that as I increase k, the radial positions of the electrons also increases.
So what I don't understand is how the picture from the clean system can in any way carry over to the argument on your left board, because it's clear that the radial dependency is just an artifact of the periodic, both periodicity and the extensiveness of the wave function around your pole, right?
Yeah.
So I mean, I really don't understand how this picture can tell you anything about this argument once their states are localized, and there's no reason for this. There's no reason for the periodicity to tell each electron where to move.
Yeah. Okay. But the heart of the argument is here, where we didn't have to know anything about the wave function. So that tells me that I get an integer. And I just wanted to understand with the calculation from the clean system in a bit more detail how that process happens. So I agree that it must be much more complicated with disorder. But in a way, the point of the argument is that I don't have to understand the details. Okay, so that was the second approach, and yeah.
Follow up to that. If I have disorder, now there's some spreading of the Landau levels. Is it immediately clear that adiabatic ramping is going to give me back the same state?
Yeah, it's a fundamental theorem of quantum mechanics that if you increase the flux by one flux quantum, you can then gauge it away, and so you have the same Hamiltonian, the same set of states.
Well, for gap systems, that's certainly true, but this is a gapless system, so it's not clear that I come back to the same state and go. essentially get narrow avoided crossings at other levels besides these edge states?
Well, of course, in a sense, you don't get back to the same system because to the same state because we're saying that this process pumps charge across the ring.
Right, but it's crucial to your claim that the bulk better come back to
Yeah.
where it was.
Okay, so in the bulk, we don't necessarily have a gap because there may be localized states at the Fermi energy. But then states which are localized at the Fermi energy shouldn't be sensitive to this inserted flux at all, because if they don't wrap around the sample, they can't tell that it's there. So what should be sufficient is not necessarily a gap, but a mobility gap at the Fermi energy, and that's the case. Okay, so now I want to talk about a way of thinking of the Hall conductance in terms of something called the Chen number, which is quantized in integer values. And the way that we do this is by thinking about the system on a torus. And some of the arguments are going to be in the same spirit as the flux insertion argument, which is to say that as well as the magnetic field, which obviously will come out piercing the surface of the torus, we're going to have two fluxes which we'll use to produce response in the system. So these will go through the two holes in the torus, and I'll call those fluxes theta and phi. So we consider the system on a torus, and to be reasonably explicit, I'll pick a gauge. And have the torus in the xy plane, and then the Hamiltonian has the usual kinetic energy terms. And then we have some random potential on the surface of the torus. And to be precise about what we're doing, we can look at the boundary conditions on the eigenstates. So if I go around the torus in the direction parallel to the non-zero component of the vector potential, then I have just ordinary periodic boundary conditions, but if I go around the torus in the other direction, then because I've done a translation and therefore change the vector potential that I see, the boundary conditions have to involve phase, and that phase is and you can check, for example, that if you want the two translations around the torus to commute, if you do them in one order compared to the other, you pick up an extra phase of e to the I Lx Ly over Lb squared, and that would better be a multiple of 2 pi, and that translates back to needing a whole number of flux quanta through the surface of the torus, which of course you could think of as being due to some whole number of magnetic monopoles located somewhere inside the torus. Okay, so the Hamiltonian, as I wrote it, was for a system in the absence of these two fluxes, but if you include the fluxes, then you get extra terms and of course you can think of that by saying that if you integrate A dot dl around the torus, then you get the enclosed flux, and you can take loops enclosing either theta or phi. And then another thing that's important is that we've got the flux dependence in Hamiltonian, and these boundary conditions are independent of what the fluxes are.
Sorry, can you explain that a little bit? Why the boundary conditions don't know anything about the flux?
Well, I could do transformations. I might be able to shift the fluxes from the Hamiltonian to the eigenstates, but
okay, go ahead.
Just for the way you've written it, it seems like the Bx is in both the Hamiltonians and the eigenstates, but the phi's and the thetas are only in the Hamiltonian. Is that asymmetry? Is there a reason for that?
It's a B delta x.
sorry, you said what is in the
Also, this Bdx term is in both the Hamiltonian and the eigenstate. It seems like you've already done the gauge transform to the eigenstate, so I should get rid of it in the Hamiltonian, or is that not true?
which term, the Bx?
It seems that by defining these boundary conditions, you're essentially sticking the gauge on the eigenstates, and therefore it should be gone from the Hamiltonian, or not about that?
No, I mean this does much more than affect the eigen. Does much more than affect the boundary conditions. So I mean, what you might like, if you could have it, would just be standard periodic boundary conditions. But you can't have that in the presence of a magnetic field, because if you translate in X, then if you've picked this gauge, then you change the vector potential. So you have to allow for that with this phase factor. But the presence of this vector potential is going to do much more than just produce this phase on the boundary conditions, because obviously it's got to generate lambda levels for us. Okay, so the basic idea is going to be to use these fluxes through the torus to learn about the Hall conductance, and The first point is that you can get the current operators as derivatives of the Hamiltonian with respect to the flux. So, for example, suppose we look at what happens when we differentiate the Hamiltonian with respect to this flux, then what we get is basically the current operator in the x direction. Times 1 on x. So if we want to calculate the average current in an eigenstate in the x direction, we take the expectation of this derivative of the Hamiltonian. So this would be the current density, and it's the electric current density rather than the probability current density because of the factor of the charge here, and is divided by 1 over Lx, but when we take this expectation value, we integrate over x, which cancels this factor, and of course we also integrate over y, which integrates the current density up in the transverse direction, and what we end up with is the expectation of the current in the x direction. Okay? So we can learn about currents by thinking about this quantity, but it's convenient to take the derivative outside the expectation value, so we can think of d by d theta of the expectation of h, and then we should subtract off the two terms where the derivatives act on the wave functions. And now, to do something with this expression, we can say that h acting on the wave function is something that we can express via the time-dependent Schrödinger equation. So we have that h psi is and then we can say that we're going to drive a current in the x direction in exactly the same way that we did with the flux insertion argument. In other words, by changing the other flux, the one that I called phi. Okay, so then we want to think about how how the state of the system will change when we're changing this flux pi through the sample slowly. And if we're doing it slowly, then we can think in terms of the adiabatic theorem in quantum mechanics. And say that the state of the system at a particular time is whatever the eigenstate of the time-independent Schrödinger equation would be with the parameters relevant for that time, so we could label it in terms of these fluxes, times a phase factor which is just the accumulated phase from the time-dependent energy. So we can substitute for H here and say that when we differentiate this time-dependent wave function, we get two contributions. One is the instantaneous energy, and the other comes from the rate of change of the instantaneous eigenvector, which will depend on the way that that eigenvector changes with the flux and the rate of change of the flux. So if I put all of that into this expression for the current, then the terms involving these energies will cancel between these two, because here I have IH bar times psi dot, and here I have its complex conjugate. So what we'll get is, from here, a term which is the energy derivative of, the flux derivative of the energy, and from here, two terms which together are, and then from here, d theta.
Excuse me.
Yeah.
Can you explain this term? Yes, that line.
So that just comes from differentiating this. And this term comes from differentiating this. So the idea is that this is the instantaneous eigenstate of the Hamiltonian, and it's changing with time because flux is changing with time.
Is there a parenthesis here? So H is multiplying psi, but E of t, I can't really...
Well, so what I had before was that from the time-dependent Schrödinger equation, I had H psi is I plus d psi dt of psi. So what I'm evaluating on the right here is this time derivative.
So there is a parenthesis acting on
That has been
state.
There's two multipliers.
Sorry, sorry, thank you. Yes, okay. Yeah. Thanks. Okay, so the idea is now that by relating the current around the torus to the parametric derivative of the Hamiltonian and driving the current by letting the flux change with time, we've come down to this expression for the current, and it obviously has terms of two types. So if we didn't make the flux time dependent at all, we'd be left with this term. So this is somehow a ground state current. Sort of diamagnetic term in the absence of any driving field. And that's not really what we're interested in. What we are interested in is this term, which is the response to the time-dependent flux that's producing our EMF. So, identifying that as the response, we can say that the Hall conductance is basically that second term. Okay, and if we stop there, it wouldn't really have been a very useful exercise. What turns it into a useful exercise is to say that we're not simply going to think about the Hall conductance at some particular values of these fluxes, theta and phi. Instead, we're going to study the quantity that we get if we average this Hall conductance over all values of the fluxes, weighting them equally. So I'll call this average Hall conductance sigma xy bar, and it's just the same expression, but now integrated over one flux quantum in both directions. So we normalize in that way, and then the integrand is the expression that I have above. Okay, and now the point is going to be to recognize that the integral that we've got is something that's quantized, and I'll go through that in detail. But are there any questions about how we got to this point?
Why are we averaging over the fluxes again?
If we don't get anything with this argument. We have to average to get an interesting answer. So, of course, the hope is that we're averaging something which is more or less independent of the phases, and then it really doesn't matter that we've averaged.
Yeah.
But
Can you come back and see that afterwards?
well, no, I think at the moment it's just an article of faith. So why should that be reasonable? Well, the answer comes back to this issue of having a mobility gap at the Fermi energies. So if states for the system are Anderson localized at the Fermi energy because we're in the Hall plateau, then they should be sensitive to the fluxes through the torus, and so then it's at least possible that this Hall conductance is independent of the fluxes. But I mean, you could turn it around and say, well, clearly I'm going to head for an answer which will tell me that the Hall conductance is quantized. At the same time, there are obviously systems out there which have nothing to do with the quantum Hall effect, which don't have quantized Hall conductance. How do they escape this argument? And you know, the way out would have to be that the value of this quantity fluctuates as you change the phases. If you don't have a mobility gap. Yeah.
Can I maybe ask a larger question?
Yeah.
Is the point of this whole argument with the torus to show that you have to have quantized Hall conductance even if you can't imagine edge states? So you're imagining some kind of completely periodic Hall system, so there's no way of thinking about edge states, and we're still going to show that you have quantized Hall conductance. Is that the point? Or is there something else that I'm missing?
Yeah, that's part of the point. You know, at some level, if you reduce the issue of quantization to something that topology tells you is an integer, then you've done something satisfying in finding a particular way of looking at the problem. But yeah, the distinctive thing that's different in this argument compared with the others is not having edge states at all.
So, can this formula be generalized to higher dimension, means 3D?
Well, this version is specific to 2D. Yeah, I mean, yes, there are things, but I'm not. I haven't prepared to talk about them today. Okay, so what remains is to see why this quantity is quantized, and that goes in a couple of steps. So the first thing is to see that the argument of this integral we can think of as a kind of generalized curl. So we can think of this as the curl of some two-component vector. And when I say curl, what I mean is if the vector has components which I label by these two fluxes, theta and phi, then the curl will be that derivative. And this all works if I make the right choice for the vector v, which in terms of its components is the first component, and then the second component is just the same, except that I swap these derivatives with respect to theta for ones with respect to phi. So now, once we see that we can think of this integral over the fluxes as the integral over curl over an area, we can use Stokes Theorem. And say that the integral is equivalent to a line integral of d dot dl. And so we just have to understand what that line integral is, and it's around the perimeter of this region that we're averaging over in the space of the two fluxes. So to understand what that is, we need to look at the components of the vector. And if I take, for instance, the first one, obviously, this is looking at the overlap between the wave function with a particular value of the fluxes and its change when I change the fluxes. And so you can think more generally about what happens to a wave function, an eigenfunction in the system, when you change the parameters in the Hamiltonian a little bit. And so some small change in the parameters will change a state from psi to, say, psi primed, and that will be close to psi with some corrections, and one of them will be something in the same direction as psi, and the rest will be something orthogonal to psi. And the coefficient of the bit that's in the same direction as psi must be pure imaginary in order that the normalization of the state is preserved. So what this means is that the overlap is simply this change in phase of the state, and this difference with the factor of a half is simply the change in phase, and then we have an I here which cancels the I. So when we integrate around the perimeter, we're looking at how the phase of the state changes as we change the fluxes through the torus. And if we go around a closed loop, this should be 2 pi times an integer, because the phase of the state should come back to what it was when we started. So
Excuse me?
if we put everything together, what this gives us is again the Hall conductance is E squared over H times this same integer. Yes?
Well, what's the last term?
Sorry, this term.
This.
This is something that's orthogonal to the initial state. So if I change parameter in the Hamiltonian by a small amount, then the phase of the state could change, which produces this term, and the state itself could change, but by normalization, this change in the state has to be orthogonal to the initial state.
Do you show it the delta psi or delta?
Yeah, so I mean what I'm trying to say here is that if we think about that normalization, which I want to be unity, then working it out to the right hand side, I have from this term 1, and then from this I have I delta alpha. And from the complex conjugate, I get minus that. And then I have 2 terms from here, which will be and then I get some second order terms. So these had better be 0 to preserve the normalization. These cancel provided this coefficient was pure imaginary as I took its period. Sorry, I think you were next.
Sorry. No, I was just wondering, this argument had 2 fluxes in it, right?
Yeah.
And we used the time-dependent one essentially to apply a Hall voltage. Do we need the other one for the argument? Is there something crucial about it? Could we have set it to 0 from the beginning and gotten the same conclusion?
Well, we averaged over it.
Oh, so it needs to be non-zero.
So we average over all values of it. And of course we use the fact that the derivative of the Hamiltonian with respect to this flux is the current operator. Yeah.
So
I think if you left it out, then the whole approach falls apart.
Yeah, I guess that if I'm just thinking about a Hall current experiment, we sort of use the one to make a Hall voltage, but I don't see any analog of the other one in like a Hall bar or anything like that.
I think you're right, and this is a theorist device, a theorist approach. Sorry, yes.
So if I want to understand this, go back to this point of the averaging. So somehow, in this geometry, we have mostly localized states, right? Because there are no edges. But as you were discussing yesterday, there is a narrow region inside, around level that has delocalized states, right? So I would imagine that those are the ones that are most sensitive to these fluxes, right?
Yes.
So somehow these are the robustness of this averaging should be tied to this statement that you made about the width of this energy region going to 0, right? This energy region of delocalized states.
Well, it's true that those extended states will be the ones that carry the current in this torus geometry, and it's true that they're buried below the Fermi energy. And because they're the current carrying states, they'll be the ones that are sensitive to these changes in flux.
Okay, so if we want this average to fail, what are like the conditions then for
Right, okay, so the situation when the averaging would fail, well, if we stick with quantum Hall systems, then we simply need to go to a filling factor that puts us part way between one plateau and the next. Then the extended states will be close to the Fermi energy, and what would happen as you change these fluxes is that then the current carried by these extended states would fluctuate as you change. The fluxes. Well, I mean, what would happen is that the current that's carried as you change the flux would be swapped between a state that's occupied and just below the Fermi energy and the state that's empty and just above the Fermi energy. There are a couple of things I should really have said at an earlier stage. I mean, this argument at the moment I'm really applying to a single particle eigenstate of the Hamiltonian, and that gives me one contribution to the Hall conductivity, but then I should add up those contributions from all of the occupied states, and the localized states will give me contributions of 0, and then the extended states can give me contributions which give me my units of Hall conductance. And then there's one more thing that I should say, but let me...
So it depends, like, the arguments relies on that I can define a state given theta and phi, right?
Yes.
And then threading theta and threading phi, do they commute? I guess they don't, right? Like in the x and y do not commute, so or
well, they're just parameters in the Hamiltonian. They're classical variables, so
but
it doesn't matter what.
But for the quantum states, it depends on the path that I take, right? How do I evolve theta and phi? I guess the states are different. Because threading this one and threading this one do not commute then the maybe I can formally define that state depends on theta and phi, but I guess it's not unique.
The one, look, I'm evolving in time phi,
yeah,
because that's the one I use to drive the current. But theta is just a parameter. And so up to this stage, I'm thinking of phi evolving in time, and then I have an expression for some instantaneous value of the Hall conductance. It just depends on theta and phi as parameters. So when I do this average over the different values of the flux, I don't think there's any issue about the path that I follow.
Oh, so they
I'd like you to understand the relation between this argument and the Laughlin argument, because if suppose we didn't have theta, then we would be precisely, or I don't know, precisely, we would just be repeating the Laughlin argument, which was to integrate over phi by saying that phi is a time-dependent parameter, and then indeed we have the charge as the boundaries of the integral, and the charge has to be quantized. So if we think of theta as the fluctuating in the other direction, so that if we integrate it over it, we shouldn't change the charge at all, right? And this is just, in a sense, the same argument as Laughlin's in a different context, right? Because I'm just saying that the charge is the boundary of the integral in space.
Yeah, but I think it's a significantly different context because the geometry of the sample really is different. It's a torus instead of this coordinate ring. So I think there's a limit to the extent to which you can hope to tie the two things together.
This argument can be repeated with other geometries. It has to be a torus.
Yeah, to get us to this Chen number, yes.
Does the fact that it has to be a torus have to do with, I don't remember exactly where I've seen this, but somehow the fact that this is like a closed compact manifold, and if you want to express this as some effective curvature, basically says that that's why the integral has to be this 2 pi times the integer. Is that the reason why it had to be a torus?
Well, there are two, in a sense, there are two toruses here. So there's the one that the electrons are moving around on, which is what I've been calling a torus all the time. But there's also the parameter space of these fluxes, which makes a separate torus. And I guess for the Chern number, the important thing is that the fluxes make a torus. Now, there's one more thing which I feel I ought to point out to you. You know, if we all had a strong training in topology, maybe I could have got to this point and then you'd have accepted immediately that this integral was going to give me something quantized. But I wanted to show that that was the case in detail. But I should perhaps comment a little bit on the expression that we're integrating. The point is, what we're doing here is looking at states as a function of these parameters, the fluxes theta and phi in the Hamiltonian, and comparing, as I explained over there, the phases for different values of the parameters. But you realize pretty quickly that there's some arbitrariness in doing that, because if I like, I can choose to give my eigenstates some different set of phases at each value of theta and phi. That's to say, I could do some gauge transformation by taking what I first thought of there and multiplying by some phase that would depend on the fluxes. And the crucial thing is that the integral is insensitive to changes of gauge like that. Okay, so I think I have time to start talking about the next topic, which you don't yet have notes for, but I think you'll get the notes tomorrow. So the next topic is to think of the plateau transition as an example of a phase transition.
So can I ask one last
Yeah,
question?
sure.
So, you know, in this argument, the current is being carried by these extended states. Like, but somehow when we were doing the argument, say in the whole bar, the current was being carried by the edges only. So
yes,
we did not include the current that was being carried by this state, right? But it should be there, right? Because it's here. Why it disappears there, right?
Right. So in the whole bar geometry, the division of the current between the edges and the bulk depends on how the Hall potential drops across the sample. And that's actually something that one can see even thinking about a clean system. So if I draw once again one of these pictures of the potential as a function of cross-section going across the Hall bar, if as I was talking about yesterday, we just imagine the Hall potential dropping at the edges of the sample, then I'd say I have one value of the chemical potential at one edge and a higher value at the other edge, and then I'd say that the current is all carried by these edge states.
So you're saying somehow that the electric field, saying the part that is flat does not really tilt this.
So on this picture, because the energy of states or the potential in the bulk is independent of position, there's no electric field. But another possibility would be that I have some gradient in the bulk as well. And so then there'll be some contribution from the bulk current. So it's hard to draw a decent picture, but the issue really is whether there's potential gradient in the bulk, and the intention here in this picture is that there's no potential gradient, and in this picture there is a potential gradient, and in the lower case there'll be a bulk current which will make up for a reduced edge current.
So, but are you stating that somehow in the whole bar geometry, the rearrangement of charges is such that there is no electric field in the bulk, that we only have to look at the edges? Or?
Well, I mean that's gets to be quite a complicated question actually, and to discuss it at all, of course, you have to include Coulomb interactions, and then you should think self-consistently about the way that the Hall potential is dropped and how the charge that produces the Hall potential arranges itself. And you can also, of course, try and measure where the current flows in experiments. And then there are quite a lot of details that become important. But luckily these arguments about quantization give you some reason to think that the actual Hall conductance is independent of the details, and experimentally you find that it's quantized to better than 1 part in 10 to the 9.
So I'm just trying to wrap my head around these 3 examples.
Yes.
What I'm supposed to take away from it. So I'm sort of convinced that it should be quantized, right? But I don't understand the fundamental mechanism underlying all 3. Is it just flux quantization? Is it charge quantization, level quantization? Are they related? What is essential?
Well, it's not really any one of those. If you could simply reduce it to one of those, then it wouldn't be something new. Perhaps the most fundamental one is this Chen number, which tells you that, if you develop it, it tells you that a Landau level carries a quantized Hall conductance, and that if you localize, the content of this result is that if you localize some of the states from the Landau level, the remaining ones carry extra Hall current in a way that leaves the conductance quantized. Yes?
Is there any physical picture that can explain we have to average over these 2 flux to get the result correct? We have to do average.
Yeah, well, it's simply that in order to relate this expression that we have at the top for the Hall conductivity to something which topologically has to be quantized, it's necessary to do this average. So it's not some physical argument. It's just that this gets us to a connection with some mathematics.
Did TKLM do that?
Yeah. So that so they did it for the Harper problem.
Sorry, I don't know if this is easy, but you mentioned that you can't formally define this Chern number for systems with open boundaries, at states essentially. Is there some easy way of seeing that the topological number still survives in these systems then?
Well, I think the kind of answer to that question is through the first two approaches that I described. The H-state approach and the flux insertion.
So where does this argument fail if psi is a localized state?
Well, it doesn't fail, but if psi is a localized state, the integer which you get will be 0.
And that would be because you can always gauge the contribution of the flux? Or?
Yes.
But the fact that we have a non-zero Chern number also means there's an obstruction to localizing all the states, right? So we can't localize everything.
So if you draw this picture of extended and localized states, where is the Chern number sitting? Some of them have 0, some of them not.
Right, so you can take a finite system, and people have done this numerically on a torus with disorder, and you can measure the Chern number of each of the states, and so you'll find that the localized states have 0 Chern number, and there's if you take states from a Landau level, there'll be one extended state with Chern number of 1, or in principle you could have states, some with larger integer Chern number and some compensating ones with negative Chern number. But those states with non-zero Chern number will be in this narrow energy interval where extended states are.
Is there any relation between the H state and the Chern number?
Well, not directly, because I think you need the torus geometry to talk about the Chern number, and then you don't have the H states. Okay, so the next topic I want to talk about is thinking of the Plateau transition as a critical point. The first thing that I need to discuss is some material which in principle could be right at the end of Anton Andreev's lectures, although I guess you won't actually have time to cover it. So if you think of what kind of description we should be looking for the quantum Hall Plateau transition, then you can take a step back and ask more generally about the kind of theoretical description which you use for localization problems, and specifically for single particle localization problems. So you can start with a Hamiltonian that has kinetic energy plus a random potential, and then Anton Andreev is telling you about diagrammatic approaches, and following that road, you can write down a field theory which would generate the diagrams in perturbation theory, and which would be a description of the localization problem. So one route that we could follow would be to think about that field theory, which is a kind of nonlinear sigma model for the specific case of the plateau transition, that's to say for the case of a system with magnetic field. I'm not going to follow that route, firstly because there certainly isn't time in these lectures, and also, to be honest, because it gets you to a strong coupling problem where we don't have ways of doing control calculations. So if you ask how we can avoid following that route, or how we can describe what's going on without following that route to the end, then the answer is that you can at least discuss what an RG description of the transition should look like. So what I want to do in the last few minutes is talk about what an RG description of the localization transition looks like, at least for the case of a system without a magnetic field, and then I'll build on that either at the end of this lecture or tomorrow to talk about how the RG description changes when we go to a quantum Hall system. So the basic point is that in place of talking about the sigma model, which is what we'd use to derive the RG equations, we can try and discuss phenomenologically what the RG equations should be like. So what the sigma model tells you is that the coupling constant that's appropriate to discuss the localization transition, at least when there's no Hall conductance, is the dimensionless diagonal conductance, which I'll write as G, and then I want to emphasize that we're thinking about a system on a certain length scale, L. So if I have a system in a general number of dimensions, then I can talk about its conductance, its conductivity on a certain scale, and then if I make a cube of this material, the conductance will be the cross-sectional area divided by the length, so I get d minus 2 as a power, and if I make it dimensionless with h over e squared, then I've written down the definition of the coupling constant that I want to think about. So the idea is that this is the correct conductance, the correct coupling constant to think about a localization transition, and we can think about the localization transition in terms of RG flow, and we can describe that RG flow by talking about the beta function. And the overall assumption is going to be that this beta function depends not on other details of the system, just on the conductance of a given length scale itself, and it's the logarithmic derivative of the conductance with system size. So, to carry on with this review, you can anticipate fairly easily how this beta function should behave, either if you're deep in a metallic limit or if you have a system that's strongly anti-localized, and then you can guess the overall form of the beta function by interpolating between those two limits. So if we ask what we expect in a metal, then the conductivity should be independent of L, which means that this dimensionless conductance goes like L to the power d minus 2. So when we take the logarithmic derivative, we get that beta is d minus 2. And if we're deep in the insulator, then the conductance is going to decrease exponentially with length scale, with the localization length setting the scale for that. And then, because the conductance decreases as we increase L, that means that this beta function is negative. So, if you sketch the behavior of the beta function as a function of G, then we have a limiting value in the metal, that's say a large G, which is constant and depends on dimension. So this is d equals 3, this is d equals 2, and this is d equals 1. And at small g, perhaps I should make this axis log g, we go to negative values. So interpolating, we have some behavior like that. And at least in 3 dimensions, we have a point where the beta function goes through 0. And what that means is that if we start at larger values of the conductance, then the beta function is positive, the conductance is increasing with length scale, and we go to metallic behavior. Whereas if we start at smaller values of the conductance than this critical one, the beta function is negative, and we go off to insulating behavior. So we can summarize that by drawing an RG flow on the conductance axis.
How do you know you're monotonic?
You don't for sure, that's a simplest assumption. But if the beta function went through 0 more than once, then you'd have more fixed points, and maybe it would be hard to imagine what the physical interpretation might be of some of those. Let me just draw this last picture which I wanted to draw. So on the conductance axis with large values here and 0 there, on this picture we have G star, and the flow is like this, and this is metallic behavior, and this is Manson insulator.
This is without the time reversal symmetry property.
Right, so this is really just telling you about some standard ideas to do with localization, which were developed shortly before the integer quantum Hall effect was discovered, and which are going to be the framework that we have to build on to talk about the Plateau transition as a critical point. Right, so, yeah.
What would be the order parameter for this condition?
Right, so that's one of the strange things about the localization problem when you try and look at it as a phase transition, that it doesn't really have something which it's easy to call an order parameter. And at a technical level within the field theory, the density of states couples a little bit in a way like an order parameter, but of course the density of states is non-critical and it doesn't vanish in the localized phase, which is the analog of the disordered phase. So I mean, the answer is that there isn't really a good equivalent to an order parameter for the localization transition, and that's one of its peculiarities.
Why the conductance itself could not play the role of an order parameter? Because it vanishes in one of the phases.
Yeah, it could, but it doesn't. I mean, normally you'd like an order parameter to be something that tells you about symmetry breaking, magnetization, which can be up and down or whatever, and the conductance doesn't do that for you.
So in the real quantum pulse system, what is the equivalence of Chern number? So what is the quantity that one should measure or think about? What is the corresponding?
Well, it's related to the Hall conductance, so I mean that's...
Isn't it somehow related again to the number of its state? Means the conductance, talking about the process,
well, we have these different ways of looking at the Hall conductance according to the geometry of the sample, and I think there really are limits to the extent to which you can simply equate them. I mean, they're linked via the Hall conductance.
But then what does G mean?
Oh, I think it's reasonable to see G as being a coupling constant for this transition in just the same way that you would talk about coupling constants in other systems. So, for example, in a magnet or a superfluid, you can talk about a long wavelength stiffness, and this conductance is just like that, and it's it flows according to the length scale that we measure it on, and that length scale is just this length here.
So can you write some free energy where it actually is a coupling constant?
Yes, well that free energy is basically the field theory, this sigma model, and it does appear as a coefficient of a gradient term in that sigma model in the same way as stiffness is in other problems.
No, but there is limitation to this description, because sigma exists when finite sample is poorly defined. It fluctuates with amplitude 1.
Yes.
So rigorously we should think of it gradually broadening towards zero, or evolution of distribution of sigma with length.
Yes.
If you really wanted to write down some kind of order parameter, you could look at long time autocorrelation functions, right? And you could treat those as order parameters for whether you're in the localized or metallic state.
Yes. I mean, what people have looked at is the probability distribution of the local density of states,
right,
which I think goes in the same direction as what you're suggesting. Okay, so this kind of is intended to set up a language, and the next step will be to use this language to talk about a scaling flow that will describe the plateau transitions. But I think since I'm already over time, I should leave that until the lecture tomorrow. So I'll stop now.